Okay, hello everyone. Today we will learn about linear models and estimation by least squares, part 6. Chapter 11.8 is correlation. And actually, when we are modeling the situation, when we are modeling expected value of y, there are two possible situations. The first scenario is that x is non-random variable case. In this case, we can control the x variable. Something like if, for example, if x is temperature settings and y variable is some income with respect to that temperature variable, then probably we can set up that the temperature setting is 10 degrees of Celsius and temperature setting is 15 degrees of Celsius and temperature is 20 degrees of Celsius, and y variable is the relative component like yield value with some for 10 degrees of Celsius, we get like 20, 25, or something like that. And so in this case, x is non-random variable case, and sometimes x is random variable case. For example, our x variable is weight parameter, um, and our y variable is height parameter. Then the weight, both weight and height are random variables, and maybe in this case x and y follows a binomial distribution, and in this case we can model the situation as expected value of y given x is x, and we can model the situation like this. Okay, let's consider the second case. For the second case, we may assume the variable x and y has a bivariate normal distribution with expected value of x is mu x and expected value of y is mu y, and variance components are like this and correlation coefficient rho is like this. And in this case, we can model the situation like this. Expected value of y given x equals x is beta 0 plus beta 1 x. And if we model the situation like this, here we can show that beta 1 is this component. I will show why it can be shown like that. Firstly, I will define some values. So let's define x and y follows normal distribution with mean mu x mu y, and variance component is sigma, which is sigma x square rho sigma x sigma y rho sigma x sigma y and sigma y square. Okay. And here this component is sigma. And actually we can define this this bivariate normal distribution using standard normal distributions. Let's say Z1 and Z2 follows standard normal distribution. They are independent standard normal distribution from normal 0, 1. And let's say the sigma can be represented as L prime, and one of the form of the L can be we can set L as sigma x 0 rho sigma y and sigma y 1 minus rho square 1/2. Yeah, let's define our L this way, and then you can check that L prime becomes sigma. Actually, L is a Cholesky decomposition of this sigma. And then if you define our x and y as this way. X and y is, this is mu x mu y plus L z1 z2. If we define our x and y like this, then we can show that our x and y follows normal distribution, bivariate normal distribution with mean mu x and mu y, and the variance component is this thing. The derivation is simple. If you take expected value of x and y, if you take expected value of x and y, then the expected value of this part is constant, and this part expected value of um, L z1 z2, the expectation goes inside, and expected value of z1 and z2 are 0. So the later part is 0, and so the expected value of x and y, this is mu x mu y. And also for the variance component, the first part mu x mu y is constant, so the variance of x and y, this is variance of L z1 z2, and the variance of L z1 z2 is L variance of z1 z2 and L prime, and this is the variance of variance of z1 z2, this is 1001. And so this is L prime, which is sigma. So we showed that if we define like this, this x and y follows normal distribution with this thing. Okay, let's move on to calculate this one in the next slide. So from the previous slide, we defined x and y this way, and here we can write x and y like this. X is mu x plus L z1 z2, which is sigma x z1, and y is mu y plus and L z1 z2, which is rho sigma y z1 plus sigma y 1 minus rho square 1 over 2 z2. Okay. So our x and y are distinct. So let's start from here. Expected value of y given x is x, is expected value of y, since y is distinct, expected value of mu y plus rho sigma y, and here z1 from this part, we can write z1 is x minus mu x divided by sigma x, and so we will write it this way. This z1 is actually x minus mu x divided by sigma x, and plus rho sigma y 1 minus rho square 1 over 2, and here we have z2. Okay, and this expectation is given x equals small x. Okay, and this expectation can go inside. The random variables here are this is our random variable, and here this is random variable. So expectation goes inside to these random variables, and mm, and since expected value of x given x is x, and also expected value of z2 given x is x, this is actually z2 and x are independent. Why is it? Here z1 and z2 are independent. Z1 and z2 are independent, and x is function of z1. From here, x is function of z1. So x and z2 are again independent, and so since x and z2 are independent, this is just expected value of z2, and which is 0. So um, so when expected value goes inside, the second part goes away. This part is 0, and so this calculation is just mu y plus rho sigma y, and here this part is small x minus mu x divided by sigma x. Okay, now it's almost done. So this one, it becomes mu y uh, minus rho sigma y divided by sigma x, and times mu x plus uh, rho sigma y divided by sigma x times x. Okay, so from this notation, we can see that this part is beta 0, and this part is beta 1. So we showed that the beta 1 is rho y divided by sigma y divided by sigma x times rho, and beta 0 is this thing. Okay. And we can also show that maximum likelihood estimator of rho is sample correlation coefficient. I will skip the details, but this is the sample correlation coefficient, and the numerator, we can check that numerator is sxy, and denominator is square root of sxx times syy. And so the sample correlation coefficient can be simplified like this. And also, in the previous lecture, we showed that beta 1 hat is sxy divided by sxx. And so, using this equation, you can also derive this part easily. And also, since we showed that beta 1 is sigma y divided by sigma x times rho, and uh, since sigma y and sigma x are fixed constant, and so testing the null hypothesis is rho equals 0. Testing whether rho equals 0 is equivalent to testing the null hypothesis beta 1 is equal to 0. Okay, so in the previous lecture, we derived that beta 1 hat minus 0 divided by the variance of standard error of beta 1 hat, which is s divided by square root of sxx. This follows t distribution with degrees of freedom n minus 2, and so if you use this relationship, you can also derive this one is equivalent. This can be rewritten to this notation, and this one is again t distribution with degrees of freedom n minus 2. Let's move on to example 11.8. The data in table 11.3 represent a sample of mathematics achievement test scores and calculus grades for 10 independently selected college freshmen. From this evidence, would you say that the achievement test scores and calculus grades are independent? Use alpha equals 0.05, identify the corresponding attained significance level. Okay, so in this case, we have mathematics achievement test scores and final calculus grade, and we want to test whether these two uh, values are independent or not. And actually, let's say the mathematics achievement test score is X, and let's say final calculus grades are Y. And we can assume a bivariate normal distribution on this X and Y. And the independence, so if we assume that X and Y follows bivariate normal distribution, then the independence implies the low parameter is 0. So the null hypothesis is low is 0, and alternative hypothesis is low is not 0. So this is the thing that we are testing, and also the alpha level is 0.05. And the next step is to decide the test statistic, which is t. We can use t as our test statistic, which is this one, and we know the degrees of freedom is n-2, and also we should decide the decision rule, which is absolute value of t is greater than or equal to t alpha over 2. So this is our decision rule, and so we have in step 1 we specify the hypothesis testing. In step 2 we figured out the test statistic, related test statistic, and the third one is figuring out the rejection region. And next step is to calculate the result, which is using R. And so using R, we put data X as Xi, and put our Y data here, and we calculate SXX, SXY, and SYY, and we also calculated beta 1 hat and n number of observation, beta 0 hat, and R. And after calculating these values, you can check the each component, and also you can calculate the t test statistic like this. So t is r times square root of n minus 2, which is this part, and divide by square root of 1 minus r squared, and this is t. And the t alpha over 2, this part is this thing. So t alpha over 2 is 2.30, and absolute value of t is 4.37, and so this absolute value of t is greater than or equal to 2.37, so we reject the null hypothesis. And this is our conclusion. In previously, one of the students asked me a question about if we are using R to answer the question, then what should I write? So if, for example, if this is an example, if this is a final exam, if I put this one as a final exam question, then what should a student can skip? Should they include? Should you include all the codes like this. Actually, that's no. You don't need to specify all the R calculations for the problem, but what you need to write is that this thing. First, you should specify the hypothesis. Like in step 1, you should specify your hypothesis and significance level, and also you should include the test statistic, like T. So you should write down the test statistic related to the question, and also you should write down the decision rule, like something like this. The decision rule is like this, and you can use R to calculate the anything, but you can skip including the code. You can just put the numbers for that, and you can just say by R. And of course, you also need to write the decision like this. We are rejecting the null hypothesis H0. And also here, the other question is identify the corresponding attained significance level, which is p-value. So p-value calculation is like this. So you can also specify p-value is 0.002, 0023 or something like this. So yeah, so solve the questions this way if you encounter these in your final exam. Okay. There's an interesting interpretation on R square. So R square can be written as this. So R is sxy divided by square root of sxx times syy. And so the square of this thing can be written as this. And from here, this one is beta 1 hat. So this can be written as like this. And this part is syy minus sse. So this can be written as this. And actually, the syy, let's say that this is SST. Let's say that syy is SST. And then SST minus SSE, actually this is SSR. The sum of square explained by regression. But before I explain what are these, I'd like to so this is SST, SSR. I'd like to draw some the geometry. I'd like to give you some geometrical interpretation about the situation. So let's say this is n-dimensional space. N-dimensional space. So the vector y is inside of this n-dimensional space, and y is y1 to yn. So that we have n components for y. So y is inside of n-dimensional space, and let's say this is subspace of n-dimensional space, and this subspace is spanned by one x1 and xp. Okay, so this one vector, this one is we have n number of ones. This x1 vector is the first column. So first explain first x variable, and this xp is pth x variable. So each of these vectors have n components, and the space of this, the spanned by this means that you can have some linear combinations of these vectors to create this subspace. That's what spanned by means. And so this is a subspace spanned by these vectors, and also inside of this subspace we have y bar here, and also we have y hat here. And actually, y hat is the projected value on this subspace. So it is perpendicular to this subspace, and y hat, this is x transpose x inverse x transpose y. So this operation is projection in linear algebra. Projection matrix. And also, what is y bar? This y bar is actually projecting y to the subspace spanned by 1, and so y bar can be represented as 1 transpose 1 inverse 1 transpose y. So this operation is projection. So projecting y to the subspace spanned by 1, and so this y bar is also inside of this subspace. So we have y bar here and y hat here, and actually let's check what's this. 1 prime 1, it is actually n, and this is n. Inverse means it's over n. So 1 prime y over n. Actually, this is y bar, and this is, so this is 1 times y bar, and so this is a vector that have y bar as their component. We have n number of y bars for this vector, and so that's what y bar vector means. Okay, and what else? And so for the triangular row, triangular inequality, if the vector for this is A, and if vector for this is B, and vector for this is C, then the length of A square is equal to B square plus C square. This is triangular inequality. Triangular equality. Anyway, yeah. If you have this, this is perpendicular, then you have this equation. And actually, this is this becomes SST, and this B square becomes SSR, and this C square becomes SSE. And so the part A can be calculated like y minus y bar transpose y minus y bar, and this C part is y minus y hat transpose y minus y hat, and this B part, it is y hat minus y bar transpose y hat minus y bar. Okay, and for these calculations in the form, it is like sum of yi minus y bar square is equal to sum of yi minus yi hat square plus sum of yi hat minus y bar squared. So this part is SST, this part is SSR, and this part is SSE. So so the total variation, sum of square total variation, can be divided by sum of square regression and sum of square error. And R square is SSR divided by SST. So this means SSR is this part divided by SSR is this part B divided by SST, it's A. So this R square, how we can interpret it is that among the total variation, how much the regression explains. So R square can be interpreted like this way. So among the total variation of Y, how much part can be explained by the regression. So this is the how we interpret R square. Okay. Let's move on to example 11.9. Refer to example 11.8, where we calculated the correlation coefficient between mathematics achievement test scores and final calculus grades for 10 independently selected college freshmen. Interpret the values of the correlation coefficient and the coefficient of determination. So coefficient of determination, which is R square, and the correlation coefficient is R and small r. This is also small r square. Anyway, the R that we calculated from the previous example is 0.838398. And from here, what we can interpret, the R, this is positive number. So the positive number of correlation coefficient implies that if the freshman with higher achievement test scores implies that they will get higher calculus grades. So there's positive correlation between the final calculus grade and the mathematics achievement test score. So what we can and their correlation coefficient is something like this. And what is coefficient of determination? We can calculate R square. The coefficient of determination is 0.7052, and among the total variation, this is SST divided by SSR. So for the interpretation, among the total variation, the variation explained by the regression, the amount is 0.7052. And that's how we interpret the result. Okay. The accompanying table gives the peak power load for a power plant and the daily high temperature for a random sample of 10 days. So we have daily temperature for 10 days, daily high temperature for 10 days, and also peak power load. Okay, test the hypothesis that the population correlation coefficient rho between peak power load and high temperature is 0. So the test is whether the null hypothesis rho is 0 versus what is alternative, versus the alternative that is it is positive. So rho is positive. This is our hypothesis. And what is alpha? Alpha is 0.05. And what is test statistic? So for the correlation, the test statistic is this thing. And for this test statistic, this is t distribution, follows t distribution with degrees of freedom 10 minus 2. So 8. And the decision rule is when t is greater than t alpha and degrees of freedom is 8. Okay, so this is our decision rule, and the next step is to calculate. So we put the data for x, we put data, and we also put data for y, and then we calculate the sum of square sxx, sxy, and syy, and also we calculate the beta 1 hat and beta 0 hat and r. And after calculating these values, we calculate um, the test statistic, which is r times square root of n minus 2 divided by square root of 1 minus r squared, which is this thing. And the value for t is 8.099. T is 8.099, and this is greater than our threshold, which is 1.859. And so we reject the null hypothesis, and so as a result we reject the null hypothesis. And also we can calculate the p-value, and this is one-tailed example, so the p-value is only this area. The value here is 8.099, and p-value is area of this thing, so it is we can calculate it like this. Okay. Homework for chapter 11.8 is this. Let's move on to chapter 11.9, some practical examples. And we have two examples illustrating the applicability of previously developed techniques to real data. Okay, let's have a look. Okay, let's move on to example 11.10. In his PhD thesis, H. Behbahani examined the effect of varying the water-cement ratio on the strength of concrete that had been aged 28 days. For concrete with a cement content of 200 pounds per cubic yard, he obtained the data presented in table 11.4. Let Y denote the strength and X denote the water-cement ratio. Okay, so in Behbahani's thesis, he experimented some condition and the cement strength. Okay, and he is going to model this situation using simple linear regression. So fit the model EY equals this thing. So to fit the regression model, we can use the formula for beta 0 hat and beta 1 hat, beta 0 hat and beta 1 hat. From here, actually, I'm showing you the code, but when this is the final exam, you cannot just write the answer like beta 0 hat is something and beta 1 hat is something. Rather than that, you must present the formula, something like beta 1 hat is sxy divided by sxx, and also sxy is sum of xi minus x bar, yi minus y bar, and this calculation is sxy is here 0.233, and so this becomes something. Beta 1 is here, which is this one, so this is minus 1.054. So if it is final exam, you should write the equation. So when you are fitting the model of this thing, I explained these using R code, so probably you can quickly get the answer from your R code. But do not write only the answer. You should write down the formulas, something like this. That's what you need to do to get 100% of the credit for your exam. Okay, so anyway, using this R code, we can calculate the beta 0 hat is this one, 2.56, and beta 1 hat is minus 1.054. And so you can calculate it using R. And about B, to test H0 is beta 1 is 0 versus the alternative hypothesis is beta 1 is less than 0 with alpha is 0.05. About the test, you should write the test statistic, the related test statistic. Here, beta 1 hat minus beta 0, beta 1 hat minus 0, divide by square root of s square 1 over sxx, something like this. You should write down the test statistic and what this distribution of the test statistic. This follows t distribution with degrees of freedom 6 minus 2, and you also write down the decision rule. So since this alternative hypothesis is beta 1 is less than 0, so let's say this is your t, and t is less than t alpha over 2, minus t alpha over 2. Oh no, not over 2, minus t alpha, since it is one-sided test. So this is your decision rule, and the next step is to calculate. You can calculate it using your R code, and from here you can calculate the value t. This is minus 11.06, so this is minus 11.06, and from this rejection rule, minus 11.06 is less than minus 2.1318. Here is minus t alpha. So the conclusion is reject H0, reject the null hypothesis. This is your conclusion. And what else? Identify the corresponding attained significance level, which means the p-value. In the slide, I missed the p-value here, but you can easily get the p-value using PT of minus 11.06, and degrees of freedom is 6 minus 2, which is 4. And yeah, that's it. Using this code, you can calculate because this is the area of this thing. So this is p-value. I think I have. Oh, I don't have the code. Anyway, using PT with this code, you can calculate the p-value without much difficulty. And let's move on to number C, which is to find a 90% confidence interval for the expected strength of concrete when the water cement ratio is 1.5. So when X star is 1.5, what is the bound for expected value of y? The confidence interval for EY, and you have the formula for this as well. So to prove this problem, you should firstly write down the formula. Like I don't have enough space, but here like beta 0 hat plus beta 1 hat times x star plus minus t alpha over 2 times s times square root of 1 over n plus x star minus x bar squared divided by sxx. So you should write down the formula first and then calculate the interval, something like this. So interval is 0.97938 to 1.020, 1.020, something like this. So this is the confidence interval when water cement ratio is 1.5. And the next question is, what will happen to the confidence interval if we try to estimate mean strength for water cement ratio of that of 0.3 or 2.7. I didn't calculate it here, but you can put 0.3 here or 2.7 here to calculate the confidence interval. However, that's not that would not be very good, because in your data the water cement ratio is about this region. However, 0.3 and 2.7 are very far from the data. So even if you can calculate the confidence interval, the result is not very helpful for your research, because the data you used for this simple linear model, the data range is something like here. But if you are calculating the data from too far from here, it's not a good idea. Okay. Okay, so far we learned this sixth part of the linear regression, and in next week we will finish the lecture for chapter 11, and we will probably move on to chapter 12. Okay, okay, thank you and see you next week.